Monsters of concrete, gigantic artificial lakes, power plants dug into the mountains or buried in the sea, hydroelectric dams beyond belief. Like the most famous one at Tignes.
The biggest dam in Europe and the third highest in the world at the time, it's a monumental work.
Behind this wall, there's the equivalent of 100,000 Olympic swimming pools. To resist the force of the water, the dam is designed with dozens of microfaults. In Brittany, there's Rance. No one imagines that hidden under this bridge is the first barrage in the world to produce electricity entirely thanks to tides, which are among the highest on the planet. If Rance is a titan of the seas, Roselend is its equivalent in the mountains. It holds the absolute record in terms of concrete. An exceptional stratagem makes it as powerful as a nuclear reactor. The water that rushes down from the dam drives wheels weighing more than 20 tons. Tignes, Rance, and Roselend. 3 dams, 3 masterpieces of civil engineering. France has a lot of dams. There are more than 650 of them. Since the 18th century, French engineers have amassed a unique know-how in the field, overcoming new challenges each time, such as filling the dam's lakes without disfiguring the landscape.
To tap water resources and rivers to feed our big dams, we dug 1,500 kilometers of tunnels. That's 1.5 times the length of France.
Once the wall is built, a gallery will make the water rush almost vertically towards a hydroelectric plant. Inside, giant turbines are driven by the speed of the water. The jet arrives at 500 kilometers per hour. The moving parts of the turbine need to be perfectly assembled.
They're adjusted to 1/10 of a millimeter, with parts weighing up to 100 tons.
It's a power-generating performance in the size XXL. In 1952, Tignes beats all records. Never before in France has a work required so much material to achieve its intended dimensions. The dam holds back a phenomenal amount of water. When the gates open, it's conducted into an underground gallery. At the plant, it would drive the turbines and thus produce electricity. After World War II, France has an ever-growing need for energy. The powers that be focus on the country's environmental potential.
The idea was, let's use what we have, our valleys and rivers.
After scanning the countryside for possible sites, the research departments are unanimous. One region lends itself to the project just perfectly. It's Savoy, and particularly the mountain area southwest of the Mont Blanc Massif.
It had been identified between the wars as an ideal site for a water reservoir.
In the Chevreul Valley, there is a river, the Isère. If a wall could stop its course, it could be used to fill the lake behind the dam. But there's another, even more potent source, albeit more than 2,000 meters high.
The main source of the reservoir is melting snow.
This combined water supply can be used to create an artificial lake behind the future wall. And there's another asset. At the end of the Chevreul Valley, the mountains form a natural lock. Yet, there's a problem. As with all construction sites in mountainous terrain, access is limited. The roads are impassable for huge trucks, cranes, and cumbersome machines. Up here, everything takes on a disproportionate scale.
Tignes is in the middle of nowhere. Bringing cement and materials poses enormous logistical problems.
So, how to get tons of material up to more than 1,600 meters? Yet, there's a solution to everything.
They built a cable car line between Bourg-Saint-Maurice and Tignes. That's 21 kilometers to lift the cement that arrived at the nearest train station.
Nobody had ever built such a means of transport over a distance like that. The cement is stored in huge silos of 4,000 tons. To transport the rocks for the concrete, giant trucks are brought over from the United States, the Euclids. They deliver the raw material from a quarry 3 kilometers away, where the blocks are extracted with a view to producing concrete on the spot.
They used more than 16 tons of explosives to extract 106,000 tons of limestone for the Tignes dam.
At an extraction rate of 400 tons per hour, the pace of the site is exceptional. However, it's dictated by the weather in the mountains. It's impossible to work in all seasons.
They only had 140 to 150 days a year to pour concrete, so they had to do as much as possible in that time.
To compensate for the delays due to snow and cold, up to 5,000 workers are brought in during the summer of 1949. It's a record in Europe. The dam proper requires gigantic foundations 20 meters deep. The equivalent of an 8-story building. Once the concrete is injected, it will cling to the hard rock below. Then the wall is raised block by block up to its planned height of 180 meters. 4 supports are added on the outside of the curve that faces the valley.
A geological study of the parts of the massif which have to resist the forces on the sides is fundamental. If it's faulty, the dam will collapse.
The foundations of the dam, as well as its links on both sides, must be solidly anchored, as the pressure exerted by the mass of water will be immense.
The lake of the Tignes Dam holds 235 million litres of water.
To counter this monumental thrust, the engineers opt for a particular design. It differs from conventional dams where material is piled up into a kind of artificial mountain. The Tignes Dam is shaped like a vault. Thus, the more pressure the water exerts, the more the dam anchors itself in the mountain. It's pushed into the rock. Yet, there's another way to relieve the pressure on the dam. André Coin is an engineer of bridges and roads.
One of the masterminds behind the Tignes Dam was André Coin, who holds a special place in the history of French dams since he designed more than 70.
He also planned another exceptional dam in the 1950s. Serre-Ponçon in the Alps, the biggest dam in Europe in terms of hydroelectric capacity. Coin's ploy to keep the wall from giving way at Tignes is to relieve the pressure by letting water seep out. At the foot of the dam, the builders dig openings to let small quantities of water through. The drains are between 20 and 40 meters long, as the thickness of the dam differs along its height.
Up at the road, it's 10 meters. Then it's widening till, on its base, it's 43 meters thick.
So it's a real pyramid of concrete that's built between 1946 and 1952. And like its Egyptian ancestors, the dam also contains hidden tunnels.
There's an upper gallery, 2 descents, an intermediate gallery and a lower gallery.
They're accessible only by the staff operating the dam, allowing them to check for any signs of water infiltration and whether the dam is still stable on its supports. Yet another phenomenon is scrutinized with even more attention. The Colossus lives, breathes, and moves permanently. The expansion of the concrete in summer, as well as the retraction at sub-zero temperatures, have an influence on the dam.
These movements are anything but negligible. When we monitor the lead weight several dozen meters below where it's suspended, we can see that the dam moves several centimeters.
There's another part of the project that's just as impressive, yet invisible.
In order to bring water from the Tignes dam from an altitude of more than 1,700 meters to the Margovert power plant, a tunnel was built, more than 15 kilometers long and 4.5 meters in diameter. Just imagine a tunnel in the mountain to reach the Margovert power plant.
It's one of the stupendous challenges at Tignes, to pierce the mountain and its hard rock over more than a dozen kilometers to create an artificial waterfall. In the middle of the 20th century, there are no giant tunnel boring machines like those considered indispensable today.
In 1947, the conditions for this kind of work were terrible.
Dynamite is used in abundance. The men risk their lives every day.
The construction of Tignes killed 60 workers, most of them miners digging the galleries.
The tunnel carries the water downward over 15 kilometers due to a slight but constant inclination. It's only on the last meters that it reaches a terrifying speed. At the exit of the tunnel, it's led into 2 steel pipes of 2 meters in diameter. They plunge towards the plant.
It's a vertiginous fall of 750 meters.
At the entrance of the power plant, the water comes rushing at 400 kilometers per hour. Yet, there's a threat. The mountain on which the 2 pipes are fixed is not stable.
It moves constantly due to the uplift of the Alpine massif.
The mountain, called Mont Pourri, advances by several centimeters each year. To avoid ruptures in the pipes, the engineers have provided bases in the slope, blocks of concrete about 10 meters deep, which move with the ground. The system ensures that the plant is constantly fed by water. Yet, once it arrives, it has to be stopped. So just like in a bathroom, there are taps, and they too are of record dimensions.
Each faucet weighs more than 20 tons. Their outlets are about 2.20 meters wide. So yes, they're very big valves indeed.
They're essential for hydroelectric production, designed to handle the tremendous onrush of water from 15 kilometers away. At 73 bars, the pressure is 20 times as powerful as in ordinary canalization pipes. To close the valve, counterweights of more than 2 tons each are used. There are 2 of them per tube. They're lifted by hydraulic jacks when opening and block the water when they are lowered. The taps feed 4 hydroelectric turbines. They have 2 wheels each, which turn a shaft with an alternator.
Each wheel is driven by 2 jets of water, each 20 centimeters in diameter. So 2 jets will hit the same wheel simultaneously with 400 kilometers per hour.
The injectors are each closed by a cone that obstructs the passage of water. They can be moved by a pneumatic winch.
When the cone is moved backwards, the water can pass. When you press it into the hole, the water is held back.
This system serves as a backup to the first tap if the water has to be stopped quickly. When launched, the wheels of each unit run at an exceptional speed. It takes 1 hour to stop a wheel once the injector is closed. A single manufacturing defect of a few millimeters could spell disaster. Yet the wheels are made to perfection. Their surfaces are as smooth as marble. And the trajectory of the water is calculated to be as efficient as possible. When the system is at full speed, all elements rotate at 428 revolutions per minute.
The rotor is linked to the shaft and the wheels, so the whole thing rotates, the two wheels, the shaft, plus the rotor. It rotates inside the stator, which remains static.
To produce electricity, the rotor is magnetized by embedding coils, which are put under a small amount of current. Another prerequisite, the rotor must be as close to the stator as possible. 10,000 volts are thus generated, a significant voltage, yet giant transformers will increase it even further.
They're enormous, several meters wide, 5 meters high, and bathed in oil. You don't find them in everyday life, only on structures like hydroelectric or nuclear power plants. They make it possible to raise the output of voltage from 10,000 to 220,000 volts.
When Tignes was commissioned, it represented 5% of the country's electricity production and 25% of its overall hydroelectric capacity. This was absolutely incredible at the time.
However, this exceptional performance comes at a price. Once all installations are in place, one last operation remains. During the dam's construction, a water outlet was left at the foot of the dam to prevent the building site from being flooded. Now it can be filled in to make the dam watertight. Then the valley will be transformed into a gigantic artificial lake.
The only problem is there's a village behind the dam, Tignes. Its 387 inhabitants were evicted in 1952 because the lake had to be flooded. And as methods were quite robust back then, the inhabitants were evicted more or less with military force. Then the church and the village were blown up.
Houses, shops, nothing remains. The Tignes Dam makes headlines the world over. After 4 years of construction, it bears witness to the prowess of French civil engineering in the field of hydroelectric plants. Yet, it's not the end of the story. In 1955, 3 years after Tignes was inaugurated, it's decided to build an even bigger dam. And so again, engineers will push all limits. Roselend in Savoy is a monster of concrete and technology. It will beat all records of size and power.
They poured almost 1 million cubic meters of concrete, 940,000 to be exact. No other civil engineering project in France has required such a quantity of concrete.
Behind the Roselend Dam stretches an artificial lake of 200 million cubic meters of water. It's filled thanks to an elaborate system of tunnels, bringing in the water through the heart of the mountains by linking rivers and lakes to the site of the lake.
There are 54 kilometers of tunnels to feed the reservoirs.
The last gallery dug is 15 kilometers long. Its purpose is to conduct the water from the dam to a hydroelectric plant hidden in the mountainside. Here, giant turbines with 20-ton wheels are driven by the power of the water. Thanks to its exceptional design, the Roselend Dam sets a new record for hydroelectricity production, 600 megawatts.
It's the most powerful gravity power plant in France.
The equivalent of a nuclear reactor. To achieve this stunning performance, the planners opt for an exceptional environment. The site is unique in France. A gorge formed by two mountain pincers provides ideal conditions for a dam. The plain behind it will be turned into an artificial lake of extraordinary dimensions. Yet, how can it be filled? The answer is a sprawling system of conducts hidden in the mountains. To connect about 15 different water intakes, the miners dig an entire network of galleries and tunnels. Outside, nothing is visible, yet deep inside the rocks, it's a labyrinth. The planners aim for nothing less than the most powerful electricity plant in France. Yet to keep the reservoir sufficiently fed, nearby rivers and streams need a complement. What configuration would allow an even greater stock of water to be obtained? Roselend's engineers have a solution, and it's spectacular. Roselend is in fact 3 dams.
Roselend is part of a network of dams.
There's Saint-Guérin at an altitude of 1,550 meters. The arch dam permits 15 million cubic meters of water to be blocked. 70 meters high, 250 meters long, in a picture postcard landscape, it's one of the most beautiful dams in France. Then there's La Gitasse. Construction of the dam starts just after the commissioning of Roselend in 1963. It's also arched, and though its dimensions are slightly smaller than those of Saint-Guérin, it contains about the same amount of water. 1.6 kilometers of galleries link the two lakes with Roselend. The ensemble of galleries amounts to a length of 40 kilometers. To avoid transforming the landscape into a vista of giant pipes, the workers have to dig deep inside the rock.
It was a classical miner's job. With hardly any light apart from lamps, they had to toil amid smoke and dust. It was extremely hard physical work.
Yet the most spectacular phase of the work is the construction of the Roselend Dam itself. It's a monster of concrete with an innovative design.
The Roselend Dam is famous for its aesthetics. It is both a buttress dam and an arch dam.
It's a perfect vault. Its purified lines evoke the volume of an immense balloon. Its impressive supports recall those of a Gothic cathedral. The mixture of architectural elements creates an impression never before seen in the history of dams.
Some people consider it to be the most beautiful dam in France. The French like to say that it's the most beautiful dam in the world.
Aesthetics apart, its shape is a necessity. The narrowing gorge may permit the concept of a dam and a huge lake behind it. However, the structure must be exceptionally large to withstand the water pressure over a length of 800 meters. Any other option would have meant reducing the proportions of the dam. But the overall ambition means they need to think big.
It's a monster made of almost 1 million cubic meters of concrete.
Never in history has a structure required so much concrete. However, it's not the vault itself that consumes most of it. The water exerts a constant thrust against its outer curve. Yet due to the rounded shape of the vault, the pressure is diverted to its side ends, where they meet the cliffs. In front of the vault, there's a giant wall, which constitutes the actual barrage. To support it, you need massive reinforcements, the like of which have never been seen before on a dam.
The buttresses reduce the pressure on the dam and redirect these into the natural ground.
32 buttresses are embedded into the hard rock for stabilization. Yet one thing worries the engineers. It's the geology of the site. If a dam breaks, it's rarely due to a failure in its structure, but to a sudden movement of the adjoining rocks. And if one flank of the mountain gives way, the water will rush in relentlessly and carry away everything in its path. So how can the mass of concrete be consolidated? The solution is on a par with the hugeness of the dam. You insert an underground pattern of hundreds of tubes.
Then you inject watertight material under pressure, either cement or other products, to seal leaks and limit water ingress into the foundation of the dam. There are several dozen kilometers of these holes to ensure the mountain is watertight.
The tubes require several months of drilling. Only then can the construction of the dam start with concrete poured on the spot. The dam takes shape. It's that of a pyramid. At its base, the dam is 22 meters wide. At its crest, it's only 3 meters. Inside, there are galleries for surveillance.
We can enter the very body of the dam and see if the drainage is working or not.
The water circulates in the galleries 24 hours a day. At this level, there's no concern. Yet, there's another phenomenon that needs monitoring: cracks.
Your house or your apartment have microcracks. So do dams, like all civil engineering structures. These cracks are regularly checked. The whole thing is alive and breathes depending on temperature, season, or the kind of filling.
Yet the sheer mass of concrete is an impassable rampart across the gorge. In 1960, the filling of the lake begins. 2 years on, the plant is ready to start the production of electricity. Although it will take until 1977 before the lake will be filled to its intended height. As soon as there is enough water behind the dam, it's possible to feed the turbines. Yet to generate sufficient power, it's essential to make the water drop as steeply as possible. An opening in the dam on the lakeside is the starting point of this waterfall. This breach in the wall is totally invisible.
It's underwater, it's always submerged. There's a big panel made of thin steel grids to prevent branches of trees, plants or rocks from being carried away.
It's a gigantic gallery that connects the water intake and the La Petite plant.
The main gallery is 4 meters in diameter and 12 kilometers long.
The tunnel is made of reinforced concrete along more than 90% of its length. The inclination of the descent is low, yet the amount of water is immense. The rocky parts of the tunnel are strengthened by steel, as the water will suddenly accelerate in the second section of the gallery. Inclination here is 40%, and the height of the drop is phenomenal: 1,200 meters.
4 Eiffel Towers down, you have the plant of La Bâtie, which receives the waters of the Roselend Dam, of La Gitaz, and of Saint-Guérin.
It's here that electricity is produced. An insignificant building on the outside, yet it hides a real cathedral of concrete in the heart of the mountain. The giant turbines of the 1960s have been replaced by the most recent technology. Today, Pelton wheels produce electricity while rotating. They're unique in France, like these taps. They're twinned for safety reasons. There's no seal inside, as no plastic or rubber would withstand the pressure. The wheels weigh about 20 tons each. It takes 10,000 litres of water per second coming out of the injectors to set them in motion. They rotate at 428 revolutions per minute, an exceptional performance. Next to the injectors, there are massive metal pieces. They're the deflectors. They move in front of the injectors when there is a need to stop the rotation of the wheel faster than scheduled. As soon as there are any signs of vibration, the deflector will divert the water jet against a wall.
When we decide to cut the machine, it takes about 30 minutes before its complete stop, as the inertia of the wheel is immense.
From under the wheel, the water is led outside the plant in a conduit over a distance of 1 kilometre. Yet the quantities are such that the engineers are confronted with a problem. How to release thousands of litres per second into the river without creating a tidal wave? The answer is a basin close to the plant.
It allows us to operate the plant at full power if required, and instead of channeling all this water at once into the river, we hold some of it back in what we call a retention basin.
It's an essential prerequisite if all elements have to run simultaneously. On average, each of the 6 units will start and stop 500 times in a single year. It calls for extreme efficiency of the wheels, but also of the alternator. While the wheels rotate in the lower floors, electricity is produced 10 meters above. The rotor rotates in the stator, a colossal piece weighing 130 tons, the weight of more than 100 cars. Thanks to the magnetic parts, the liquid and mechanical forces are transformed into energy almost instantly.
The electricity that's produced at the alternator level passes through what we call bus bars, big copper pieces that lead the electricity to the transformer's entrance.
Inside these blocks, there's oil, windings, but there are also cooling circuits if any problems should arise during production. It's necessary to be able to control the heat released in case of sudden breakdowns. Yet here too, the water from the mountains is an asset.
Once the water has passed through the turbine, pumps in the evacuation canal allow the water to be pumped into a buffer basin a few dozen meters above the power plant.
The use of water already turbined to cool the power station is one of the keys to the plant's fantastic annual output. La Bâtie beats all records of productivity. 600 megawatts in less than 13 minutes. The equivalent of the domestic consumption of all of Savoy over a year, as much as a nuclear reactor. If Roselend is a formidable green energy plant, another megastructure could steal its title, and it's anything but ordinary. In 1961, engineers invent the invisible dam. The barrage of Rance is an underwater colossus of 750 meters.
The tidal power plant of Rance was a world first. Since it's underwater, it's totally integrated into the landscape.
For most people, it's just a bridge. They don't suspect what's underneath.
The output of the plant is the equivalent of the consumption of a city of 220,000 inhabitants. The construction site is considered one of the most astonishing choices ever. It was decided to block the Rance estuary to build a gigantic barrier and to install the largest number of electric turbines in a single plant in France.
In general, there are 3 to 4 per dam.
At La Rance, there are 24. For the first time, electricity production is based on using the tides. The barrage seals off the sea from the landward side of the estuary. If the sea level lowers during a tide, the mass of water behind the wall is not affected. The result is the most significant difference in the water level on both sides of the dam.
13.5 meters. That's a 4 to 5 story building. It's colossal.
The height difference and the added power of the currents provide an enormous onrush of water. It drives wheels of 4 meters in diameter connected to an alternator. Thus, electricity is produced. It's a process unique in its dimensions.
It was the first tidal power plant in the world, and there's only one other, built in South Korea in 2011.
And for a reason. Few environments are as favorable as here, between the cities of Dinard and Saint-Malo.
It's the site best suited for this kind of installation.
The plant is intended to serve as the main supplier of electricity for Brittany. Thus, apart from the strong tides, closeness to the consumer is another asset.
The work was monumental, taking from 1961 to 1966.
Phase 1 is paramount. The workers need a dry site, as it's impossible to handle heavy loads in water, let alone to install electrical equipment in permeable surroundings, or to have the men work in diving suits.
The challenge was to keep out the river, to get a dry site for construction on its bed.
Yet how do you block an entire estuary? How do you enable trucks to maneuver 20 meters deep on the bed of the river? Nobody has ever achieved such a feat. A French engineer takes up the challenge.
Albert Cacot is considered one of the greatest engineers of the 20th century.
He had the remarkable idea to say, we're going to clear an area of 10 hectares in the open sea.
And so he invented the famous Cacot caissons, cylindrical columns 9 meters in diameter, prefabricated on land and towed right where they should be.
They're hollow caissons which, when inserted into the ground, allow workers to descend thanks to a pressurized system.
When weighed down with sand, the caisson became a block against which the tide could do nothing.
When all caissons are in place, the space between them is sealed off by steel planks.
They're extremely strong metal barriers which prevented the water from entering.
Once the partitions are all tied up, the water is pumped outside.
Cacot's feat is to have imagined a design that had never been implemented before.
The idea to drain a part of the estuary grabs headlines around the world. Engineers from all continents are impressed by what they see.
Emptying 700 meters of an estuary to build a power plant had never been done anywhere before.
Up to 1,000 men are working on the construction site, and they're up against a multitude of tasks. To run the plant, you need control rooms, heavy machinery, and technical cabinets over hundreds of meters.
With its multitude of galleries, it's a kind of Swiss cheese underwater.
Once the infrastructure is in place, it's time for the next crucial step: the arrival and the installation of the power units.
The machines at Rance are colossal. Each of the 24 turbines weighs just under 500 tons. They dug 12 meters below the sea floor to anchor the dam and install the turbines.
When you pass the bridge linking Dinard to Saint-Malo, it defies imagination that underneath there is a gigantic building 30 meters high. The 24 electric units are inserted in thousands of tons of concrete. Each is made up of a wheel of more than 5 meters in diameter. When hit by thousands of liters of water in a few seconds, they start rotating at nearly 100 revolutions per minute. A performance achieved thanks to the movement of the tides. All you have to do is open the gates when the tide is at its lowest. The water blocked on the other side of the dam then rushes into the turbines.
Even if we have to remain humble in the face of nature, knowing that we cannot dominate the force of the tides, we manage to channel some of the energy to benefit from it and produce electricity.
The mass of the 5-meter wheel and its blades is 80 tons, the equivalent of 50 cars. Its elements have been assembled with maximum precision.
Between the wheel and the hydraulic conduit, there are just 4.5 millimeters.
To make these machines run so precisely, this is a great feat. The more so, as in the 1960s, there were no computers to help with the calculations.
Everything was done by hand. It took an incredible number of equations to find the best way to recover all this energy.
Once the wheels are in place, huge blades are put in front to regulate the flow of water.
When closed, they overlap each other so that the water supply can be cut off completely.
When there's a need for maintenance, the facilities must be protected from water. The blades then form a shield. Inspection requires quick and safe access for the technicians.
Behind this 5-meter diameter wheel, there's the body of the machine. Even if the cofferdams aren't closed and the conduit is filled with water, we can go down into it just like into a submarine.
To avoid any water infiltrating through small breaches in the concrete, the premises are pressurized to 2 bars. Sensors check the temperature, the vibrations of the unit, and a multitude of other data. Yet, visual verification remains essential of the machinery as well as of the overall structure. The concrete vessel is pierced by galleries to check if the dam is holding up well. As it's subjected to the highest tides in the world, it requires constant control.
Thanks to the measurements we take every week, we can see that the dam lives according to the tides.
So the dam is solid. The turbines, however, are more fragile. Exchanging a part is a long and complex process. It's necessary to raise the cover above the unit and to remove the elements one by one, an operation which takes several months. Just as it was when assembling them in the 60s. After 5 years, it's time for the final verdict, the launching of the power plant. Work on the dam is finished. The protection wall of Albert-Cacot can be removed.
When all the caissons were dismantled, the passage was free again.
On November 26, 1966, the day of commissioning, the wheels work perfectly. They turn the huge stators in each of the 24 rotors of more than 100 tons. Everything's set to produce energy. Yet it's still necessary to inject a light current in front of the 5-meter wheels, as the very site of the plant poses a problem. The turbined water, unlike that behind the dams in the Alps, is salty.
We're working with seawater which enters our machines unfiltered.
Sand, salt and other agents specific to seawater will attach themselves to the blades.
It causes abrasion, like sandblasting. It can also corrode the material, make it rust.
We tested different options, coatings with special paints, as well as a choice of special metals to see how they would react.
The final choice is electrolysis. An electric current is sent into small plates in front of the blades. They attract the corrosive elements. It's a known effect, but it had never been used on this scale.
Back then, the dam was truly innovative.
The more so as the engineers went even further in the management of the water levels. The power units will not merely produce electricity, they will also serve as pumps. They suck in water to accelerate the tidal difference on both sides of the dam.
When the levels are fairly equal, we can increase the amount of stored water. It's like adding gasoline to our reservoir. The same machine that's acting as a turbine can be switched to rotate into the other direction and becomes a pump.
It's a world first.
To obtain an even greater difference in level between the two sides of the dam, water is pumped from the sea when its level goes down during the tide. Thus, the estuary side becomes a reservoir. As soon as the difference exceeds 10 meters, the gates are opened and the water flows back into the sea while passing through the 24 hydroelectric turbines. Yet the machines are subjected to violent onrushes of water. As the scenario occurs twice a day with the rhythm of the tides, it requires an exceptional quality of manufacture and maintenance.
They are pushed in one direction when we are turbining, and they are pushed in the other direction when we are pumping. So they must be able to adapt to completely different modes of functioning.
Since 1966, the Rance dam provides 500 gigawatts per year. That's 17% of the electrical energy for the whole of Brittany. Unlike other so-called green energies such as wind power or panels capturing the sun's rays, the Rance dam has a decisive advantage.
Lunar energy is much more predictable than solar or photovoltaic energy.
Forecasts predict the levels of the tide in the estuary 1 year in advance. They're monitored around the clock. Thus, the output of the plant can be constantly adjusted to the amount of electricity needed. Energy-hungry nations around the world look at Rance with envy.
International interest was immense. Delegations from at least 50 countries visited the site.
Yet investors were quickly disappointed. The concept defies duplication. Its prerequisites are too numerous. Closeness to the intended consumers, a strong variation of the tides, an estuary neither too deep nor too wide. The combination proves too complex. Only South Korea will succeed with a copy 50 years on. In the world of hydroelectricity, La Rance remains a legend.
You just open the valve, and a few minutes later, you'll have all the power of those hydroelectric turbines.
The Dam of Tignes, at 180 meters, the highest in France. The underwater plant of La Rance, the first in the world activated by the movement of the tides. The Roselend Dam, a network of dozens of kilometers of galleries built in the mountains. 3 record-breaking dams. They were designed to last 100 years. Yet their solidity and their exceptional output will enable them to operate much longer.